Alright, this video deals with bases other than E and their derivatives and antiderivatives. So now let's take a look at this. So now we're saying, suppose f of x is an exponential function, not the natural exponential function e, which is an exponential function. But now we're dealing with things like 2 to the x or 3 to the x, something like that. And then now we're also dealing with logarithms that are not natural log. In other words, they're not log base e. So this is essentially every scenario but not e, because we've already covered that. Now here are the formulas. These two formulas on the right are on your formula sheet, because technically if you have the formula for a to the u, then you also have it for the same thing as a to the x. And I'll show you what I mean here in a second. By that's why we don't need these other formulas. So I mentioned here the derivative of a to the x is a to the x ln of a, written this way or either way is fine. The bottom way kind of makes sense. That way you don't have to really use parentheses. But if you come over here and look at this, you see this says if it's a to the u, it's a to the u ln of a du dx. Well, if u is x, then du dx would just be 1. So then that's why it would just end up being this formula right here. So that's why the formulas over here to the right, u pretty much covers everything. So if we have the derivative of log base a of x is 1 over ln of a times x, all in the denominator, or it could be written this way, x ln of a, either way. Here it is in terms of u. So you see the only difference with the u is it just has du dx there at the end of it. Because of the chain rule, you always have to take the derivative, whatever that u is. And it looks like just for grins, I proved the a to the x one using logarithmic differentiation, which we are going to use again in this section. That's where you take the natural log of both sides of this. So you have ln of y equals ln of a to the x. Now log properties, it allows you to bring that x down, so the x comes down, and then we have d dx, we're taking the derivative with respect to x of ln of y, and we've done this before. That produces y prime divided by y every time. All about the chain rule. If it was d dx of ln of x, it would just be 1 over x. But if it's a different variable, it's got to be that variable prime over that variable, so y prime over y. And on the left side, the derivative of x is 1, but you have the ln of a multiplied there, so it stays there. So we have y prime divided by y equals ln of a. So you bring the y up, like here, and the last step is always to change it back to x, whatever it was originally. So we replace y with a to the x, and so there you have it, a to the x ln of a. And then I just did the same sort of technique there for the log, which you aren't responsible for proving these on a test, but I'll just kind of skip past that, and you can look at it if you want to. If you don't, that's fine too. So now let's practice using these formulas with some actual derivatives. So let's say we have y equals 3 to the x squared. Let's find y prime. So with these kind of problems, when you have a numeric base like that, this term, as we've seen with e before, when you take the derivative of e, you've always got e in the answer. Same thing here. So we're automatically going to have, if we're taking the derivative of 3 raised to the x squared, we're going to have 3 raised to the x squared as part of our answer. We just have 2 other pieces that join it based on this formula right here. So you see the a to the u has the a to the u. You put ln of whatever the base is, which is 3, and then the derivative of the u. So the derivative of x squared is 2x. And don't try to get too cute with this, because as far as trying to simplify and combine any terms there, you cannot. There's nothing there that can be combined. So it's better to leave well enough alone. In this case, it would be wrong if you didn't leave well enough alone. So how about this one? Log base 5 of cosine of x. Find y prime. So now we're using this formula. So it's 1 over, I don't know why I split these up, but obviously it's right if they're split up or in one fraction. I don't know why I did it that way, but anyway, that's okay. But it does, it's 1 over the u, and then ln of whatever that base is, 5, that's on the bottom. So ln, that's your base, 5. And then right here at the end, we have the derivative of whatever this argument is. So the derivative of cosine is negative sine. And, you know, this answer's fine. That's why I kind of gave a seal of approval here. Maybe in a multiple choice format, it might be combined, but in other words, negative sine divided by cosine does equal negative tangent. So both of those are correct. One of them just a little more simplified. Now, how about this next one? Got a product rule, 2 functions of x multiplied together, so we'll bring back our old friend, the product rule, which you see I have written there. That's the order I usually do it in, but if you do the fg prime first, nothing wrong with that. In fact, on a test, if you're trying to put product rule, keep in mind if you're checking your answers, if it's multiple choice, the order you do it might be the reverse of the way it is on the test, but that should not be a difficulty. If you do it right, you can then see, you can reverse it after you've done it. So we have f prime, the derivative of x would just be 1, so that's why you see nothing there. And here's g, so the 6 to the negative 2x, plus df, which is x, times the derivative of 6 raised to the negative 2x. Okay, so here we go, using this formula. So 6 to the negative 2x goes there. We have ln of that base 6, and then we have the derivative of that exponent. The derivative of the exponent, negative 2x, is negative 2. And once again, don't do anything crazy. Like Stewie's telling you here, don't do this. You cannot multiply those together. It looks like you can, but you absolutely cannot do that. So leave well enough alone. Now notice I have parentheses around this. The only way you could move the negative, I wouldn't do anything personally, but if you did move the negative 2 out there in front of the x, you could drop the parentheses by changing the addition to subtraction, but I wouldn't worry about it. But that's what Stewie's saying here is very important. All right, here's another product rule using alpha as the variable of all things. That's kind of rare. You wouldn't see that too often. Product rule again. So we have f prime, which is this function here. No, I'm sorry, f prime. I was thinking fg prime. No, so we are taking the derivative of this using this formula. So you see there it is. And then we have ln of the base, which is 5. So ln of 5. And the derivative of negative alpha over 2. That's the same thing as saying negative 1/2 alpha. So therefore, the derivative of that would just be negative 1/2. And then times your g, which is sine of 2x. So there's the f prime g part, all that right there. Plus f, which is 5 raised to the negative alpha over 2, times the derivative of sine of 2 alpha. Don't forget the chain rule. It's easy to want to say cosine of 2 alpha, but actually it's 2 cosine of 2 alpha. We do not want to forget that too. And once again, don't get cute there combining terms. You're not going to need to. I guess the only thing you could do, I still wouldn't waste my time doing this, but at least wanted to mention it, is that you could factor out that 5 to the negative alpha over 2, but I wouldn't worry about it. But it would be correct. All right, similar to the section on finding the derivative of the natural log, we're going to use this same kind of process, even though it's log base 7 this time instead of ln. So for these kind of derivatives, see log properties, as I mentioned before, we haven't had it yet. We were only using ln's, but those same properties apply to a log with any base. So since we have division here, we've learned before that anything in the numerator is going to be plus, and anything in the denominator is going to be minus. So I'm splitting this up using log base 7. So there's the first term, x squared plus 3 to the 4th, plus log base 7 of tan of x, and then minus log base 7 of the square root of x. Now we're going to bring down any exponents we can bring down. So this 4 will come down. Nothing happens with the middle part. And then that's x to the 1/2, so the 1/2 will come down. So we have this. So now we're ready to take the derivative. So the derivative using the log rule right over here. So it's 1 over u, which is this for this one, it's x squared plus 3. ln of 7's on bottom. This 4 was already there, so it stays there. And then times the derivative of x squared plus 3, which is 2x. I guess I didn't bother to rewrite this entire answer just to change 4 times 2 to 8. But I also didn't want to just write 8x there and people wonder where it came from. But then it's easier to look at for a student to look at it this way and infer that, that's going to be 8x. All right, so let's see. So this one we have tan of x this time on the bottom with ln of 7 on the bottom right there. So now we have a new u. And then on top we have the derivative of tan, which is sec squared. That's good. So over here we have 1/2, which I could also drop the 2 down to the bottom. Either way is correct. Either leaving a 1 on top, putting a 2 to the bottom, or like this is fine. On the bottom we're going to have x. And then we'll have ln of 7 on the bottom again, always. And then this one, the derivative of derivative of x is 1. So there's nothing else here on top other than just the 1/2 that was there. So if the 1/2 hadn't been there, we would have had a 1 on top. So that takes care of that one. It's not too bad. Just got to break it down into individual pieces and follow that log rule. Now it's, one thing I'll mention about these two formulas. Let me scroll back up there for a second and I'll come down. These formulas also work if you did for E and ln, because if you replace A with E, what happens is ln of E equals 1. So that part just goes away. So if this was e to the u, which we've already learned, the derivative is e to the u du dx. That just goes away. And then if this is log base e, which is ln, of course, so log base e, that makes this go away. And then we've learned that before that the derivative of ln of u is 1 over u times du dx. So also this, even though we're introducing these now, if you just put e in there for a, they are also those derivatives, because e is a numerical base. All right, let's try this one. Let's see, so d dx of log x cubed plus 2x squared. Okay, that's over here. I wrote this over to the right. It goes back to basic ideas behind logarithms. Perhaps you've forgotten this, but now you'll see it. Anytime that you do not see a base there for a logarithm, it is implied base 10. It's kind of like when you see a radical and there's no number outside that radical, that's implied square root. So same thing here. This is implied base 10. So there is, you might think, hey, there's no base there, but there is base 10. So ln of 10 will go on the bottom. So then you just have on the bottom you'll have ln of 10. On the bottom you'll have this part, x squared plus 2x cubed plus 2x squared. And then on the top, you'll have 3x squared plus 4x. And there you have it. No need to get too cute with this. But I will mention, I'm not saying you would have to do this, but technically, you could factor an x out of the numerator and the denominator and cancel out an x. So I thought I'd say that, but not a big deal. All right, this is interesting. I'll bring back, see if I can get the notes of 5.1 to come up here for a second. Refresh our memory on something. Let me scroll down here. The logarithmic differentiation technique. Yes. Now we did this a while back where you can use logarithms to help if you had a derivative that was a big mess like this. But notice the original problem didn't have any logs in it. In other words, this is not a log function right here in front of all this. But you use logs to simplify it and break it down. But technically, though, the idea is that you didn't have to do it that way. It was not required. But it makes it easier, I think. But yeah, you could still take this problem right here, and do a quotient rule, then you got a product rule buried within the quotient rule. Yeah, so mathematically you could work that out without this technique. So the reason why I'm emphasizing that is because now I doubt reality you'll come across these kind of functions, but I'll put these, questions on a test, so you should have this probably on the test, and maybe once on the final, maybe once on exam 3 and once on the final, possibly. I don't know off the top of my head on that problem list if it's on there or not. But this kind of, you're probably not going to see this too often, but it's going to help us use this technique. X to the x, or x to the x cubed, stuff like that, where you have a function of x raised to a function of x. So throughout this calculus course, early on in derivatives, we learned how to do like x raised to the third power, where you had a variable base and a numerical exponent. In this section, well, technically starting with the e, actually, but let's just say in this section, we're now learning, a to the x. So, we learned how to take this derivative, x to the n, where n is a number, and then now we have a, let's say, like obviously this could be a u here, but the point is, so the variable is the base, and what we learned in the beginning. Now the variable is the exponent. Well, for this one, there's variables in both the base and the exponent, and there are no rules for this. Like we have a power rule for this one, and we just have a rule we saw for how to take the derivative of this one. There's no rule. We have to use logarithmic differentiation. In other words, there's not a formula, but we do have a technique that we can use to do it. So this is no choice, like I showed you earlier for the other section there, that you could do those derivatives without doing this. But no way here. You have to use logarithmic differentiation. So we have y equals x to the x squared. Now, one thing I'll tell you is we'll go through this process here, but just like this does share one similarity to, like if you were doing e to the something or a to the something, like we just saw a little while ago. And what it does share is, even though it doesn't have a formula, is it shares the fact that whatever you're taking the derivative of is part of the final answer. So they will share that. But you'll see how that develops throughout the process. All right, we're going to take ln both sides because we need that exponent to come down. Now, when I say exponent, I mean the x squared, not necessarily the x, not the 2 from the x squared, just the entire x squared. I can see that might be a little confusing looking, but no, you're just bringing the entire x squared down, but then we're not bringing the 2 down. Okay, so just the x squared comes down. So that comes down. Now we do our ddx business, which on the left side is automatically y prime over y. But on the right side, you're always going to have a product rule here when you do this. This will be a product rule. So I did f prime, and mine actually will match Maple by doing f prime g, but the derivative of x squared is 2x times ln of x plus the f, which is x squared, times the derivative of ln of x, which is 1 over x. And then so you can bring the y over. Now it's times all this. That's why I'm using parentheses. When the y comes up, it's times all that. And of course, you might as well go ahead and simplify that x squared divided by x would just be x. So when that y comes up, we just about have it. So in the very last step, then we'll be replacing y with what it's defined as originally. So that's why the x to the x squared comes back into the final answer, because you're always going to have this y prime over y. The y is going to come up, and then therefore what you started with will be part of the answer plus some other stuff. Now, a lot of times these answers are going to kind of look ugly, but the good news is you don't really have to simplify or do anything to it. Just looks, it's a little unpleasant looking answer, but then we just leave it as is and mind our own business and go from there. So yeah, they might not be the prettiest things in the world, but who cares? So now we have this one, y equals tan of x raised to the 1 over x. So I'm going to ln both sides, which is going to bring, oh, there it is. I went sideways one step. Okay, no problem. Which that brought this 1 over x down right here. Which that 1 over x, what I did is I didn't actually show it in writing, but I can tell what I did here. Is just think of that 1 over x being x to the negative 1. I didn't want to use a quotient rule. I just wanted to use a power rule. Yeah, it'd be kind of silly to take the derivative of 1 over x using the quotient rule. You could, but it seems pointless. A lot quicker to call it x to the negative 1. So then I go f prime, which will be the derivative of x to the negative 1, will be negative x to the negative 2. times g, which is ln of tan of x. And so then you have the 1 over x to the negative 1 is your f, times the derivative of g, the derivative of tangent secant squared. So I kind of skipped a step here, but the step that I skipped is not that big a deal. I just brought the y up and then replaced y with what it was originally. So that's the only thing I left out, is just showing you the y coming up here and then replacing the y with this. So you see that what we started with is part of the answer. So that's kind of ugly looking, but who cares? Okay, here's Maple's answer. Maple did it kind of weird. How they do it, I don't know. But anyway, this is correct. It's 1 plus tan squared is sec squared. But we did get it right. So like I said, I think it's sort of beautiful in its ugliness there. So since we don't have to worry about doing anything to that. All right, here's another one. Y equals ln of x raised to the cos of x. So we're going to ln both sides. Brings the cos of x down. So we have ln of y equals cos of x times ln of x. So yeah, it's kind of weird, isn't it? But that's right. It's ln of x, as the cos of x comes in front of that. Now we do our d dx thing, which gives me y prime over y on the left. And then what do we have? Product rule is always, these kind of problems will always be a product rule. So derivative of cosine is negative sine times ln of x plus the cosine times the derivative of ln of x. So the way we would do this is the derivative of ln of x would be, it's the derivative of ln of x over ln of x. Remember, it's u prime over u. So the derivative of ln of x would be 1 over x over ln of x. So once again, I skipped the step of actually physically showing the y, the variable y, come up there, but I did put what y is right there. So this, obviously, that was the y right there. Ln of x raised to the cos x, and then times everything I have in that bracket. And let's see how we did there. So of course, this was fine the way I had it. Well, actually, it wasn't fine until I got this part in there. But as I brought this in, I decided to go ahead and drop the x down to the bottom with the ln of x. It wasn't mandatory. I just did it. Didn't mean it was wrong this way, but I just went ahead and put it down there. So, oh, how does our answer look compared to Maple's answer? This looks pretty good, doesn't it? Right on the money. Terrific. Here's another one. So we have x cubed raised to the sine of x. So we ln both sides, brings the sine of x down. So we have ln of y equals sine of x times ln of x cubed. Now, because it's ln of x cubed, you know, you're not cubing the ln here. I can bring the 3 down. I didn't have to do that, but I just chose to. So I brought the 3 down. I always like to simplify a log. Makes the derivatives and stuff easier if you simplify it. Brought the 3 down. Now, you know, you could have done this one of two ways, is you could have left the 3 factored out and then did the product rule here, but I didn't want to have to worry about that being factored out and possibly having distributed. So what I'm doing here is I'm letting that, all of that, I'm keeping the 3 with the sign, I'm letting that be f, then I'm letting this be g. So instead of leaving that as a multiple outside, I'm just going to go ahead and leave it attached to the sign, and that way I don't have to worry about any distributing or anything later. But, you know, obviously I could have done it that way with distributing, but. All right, so d dx, that's our usual y prime over y. So the derivative of 3 sine of x will be 3 cos of x times ln of x plus df, which is 3 sine of x, times the derivative of ln of x, which is 1 over x. Okay, that's okay. Now this one I actually showed the y coming up there. I did in the last couple of them, but oh well, there it is. Brought the y up and then replaced the y. Nothing happened in here, stayed the same, and then replaced, you know, our original function there, right over there. As we've been saying, we know that's going to be part of the answer, x cubed to the sine, raised to the sine of x. which would actually, that would be the same as x raised to the 3 sine of x. I guess I could have just yeah, I could have just had the problem done this way. That's true, and it would be the same answer. So like that would be the same. That's okay. No need to go back and change anything. But in case you were curious, that is correct. And then there it is. And do this one in Maple. I think I'll take a second here just to kind of show you this in Maple. All right, let's see. ddx of x. I'll put this in parentheses. X raised to the 3rd, and then I'll now raise that to sine of x, and see what we get. And I want to copy this, and then we'll look at my answer. That way I don't have to toggle back and forth. I think this should be okay. But we shall see if there's anything wrong with my answer. Oh. So how do we do here? I like it. You see what they did in Maple? This one, okay, which obviously these are equivalent by log properties, but they, yeah, that's so that the R3 is right here, but yes, so the 3 could have come down and matched my answer. So this is correct. Good for us. All right, show you a couple of these, and we'll end on this note. So I don't spend a lot of effort on. We've already done most of the time. You'll be integrating functions of e if you go further in calculus, but obviously it's good to take a look at this. But same kind of technique that you use for integrating e will work here. There's only one slight difference. That's why I don't need to spend a lot of time on this, because the only difference is that the integral of a to the u du is just 1 over ln of a to the u du. So once again, that's why this works. If that was e, ln of e would be 1. That would go away, meaning the integral of e to the u du is e to the u plus c. We've already seen that. So it's not a big adjustment to do this integral. You know, it kind of follows right off of e to the u. All right, so we just have the 1 over. Do we just have to have the 1 over ln of a in there? Okay, so here's, our base is 6 right here instead of e. So we'll have an ln of 6 in there. If u equals x plus 4 squared, take the derivative, bring the 2 down, that becomes exponent 1. I just wrote that 1 there to show you that I did not forget about the chain rule. I just wanted to write that there. Obviously, I didn't have to write it there, but I was thinking about the derivative of the inside. And then, but I only need an x plus 4, so I divide both sides by 2. So 1/2 du gives me my x plus 4 that I need with my dx. And then that'll just be 6 to the u right there. So my integral becomes 1/2 on the outside, 6 to the u du. So we just follow this. So we have 1 over, put the 2 on bottom. You could have left the 1/2 on top. That's fine, but I'll put 2 on bottom. And ln of 6 from this formula right here. 6 to the u. Then, of course, you always have to change, back to your original variable. So u is x plus 4 squared. So I changed it, and there's our final answer. So you see, this is not that bad. It's just a slight modification to the e that we've already learned. Fantastic. And the last one. 2 to the sine x times cos x dx. Really pretty easy here. Very easier than the last one, probably, because you don't have to even adjust for the du. Obviously, u's got to be the exponent, sine of x. That makes, and du turns out being cosine of x dx, which fits perfectly. No adjustment necessary. So literally our integral just becomes 2 to the u du. So you just follow the formula. So it's going to be 1 over ln of your base 2. So it's 1 over ln of 2 times 2 to the u plus c. And then replace u with sine of x. So your final answer is going to be 1 over ln of, or you could write it as one thing if you wanted to. In other words, the 1 doesn't have to sit there by itself. You could make it 2 sine of x raised to the sine of x over ln of 2 if you wanted to. That's fine. Plus c. And that's it. That takes care of this section, this video on bases other than E.